Today we're going to talk about more conceptual things, and that specifically is an introduction to fatigue analysis theory. So this might be a 30,000 foot view, or maybe a little lower, 20,000 foot view, or maybe even a 10,000 foot view of what is fatigue life, and how can we use engineering analysis techniques to estimate fatigue life for the product we're trying to design. Our agenda looks like this. We're going to start by asking a question, what is fatigue? After all, we need to be able to understand what a problem is before we can begin to try to answer it, to solve that problem. So we'll have a definition first, what is fatigue? Then we'll move on to looking at one of three different methods. We'll look at these one at a time. First, the stress life method. Secondly, the strain life method. And lastly, the crack growth method, all of which are ways of trying to understand product life. How long until a crack begins, or how long until a crack that has begun becomes a serious problem. So we'll look at those three methods. Then move on to looking at how do we use those methods in any type of a fatigue calculation. This will lead us into questions and comments about cycle counting, about Miner's rule, about damage and damage accumulation rates, and so on. And at the very end, we'll finish up with a 5 or 10 minute demonstration of how we can put these techniques into action using nCode software. So to get started, first of all, let's look at this. What is fatigue? Here are some examples of fatigue. Fatigue is a failure mode that we need to guard against. We're not going to have a lot of detail on all these, but let's take a look at a couple. First off, this one up here. This is the Aloha Airlines jet, the cabriolet version, as some people are fond of saying. This is an aircraft that, like any, because of takeoff and landing cycles, sees an expansion or overpressure, and then under pressure or pressure fluctuation cycle. And over time, those cycles and stresses can lead to failure. Fortunately, this is not a catastrophic failure. Amazingly, this plane managed to land. One person died as a result, but the pilot was able to maintain the safety of all the other passengers. This is another fatigue failure. This is a spring in a car. This spring got into a bit of a disagreement with itself and decided to split in half. A spring is a great example of something that sees a fatigue load because by its very design, it's meant to be cycled through stresses or through large deformations. Each cycle can lead to an accumulation of what we call fatigue damage and can lead to progressive failure. Down here, this is a train. As you can see, this is a train actually that's not doing very well, so we definitely don't want this to happen. This is a train that tragically crashed and killed a number of people because of a failure in a wheel. This particular wheel could pick up hundreds of thousands of cycles per day through rotation. Every rotation of the wheel was another fatigue cycle, and while the stresses weren't very high, the number of cycles that accumulated over time became a serious problem. This one up here, this is the Bay Bridge out in San Francisco. This is a large structural member. This is many feet wide that we're looking at here. A structural member that ties the road surface, the bed, up into the tower to provide that the load carrying capability. This crack is big enough to put your hand into and may have resulted from any type of structural load fluctuation, or actually it's very interesting on a bridge. Stress cycle, a very common stress cycle on a bridge, is due to temperature. Heat up and cool down once per day. Cool at night, and a hot or hotter solar load during the day causes the top of the bridge to expand relative to the bottom and can cause huge stresses. We'll talk a lot about stress cycles and what causes them and the impact of them as we look to the rest of the day today. This here is a wind power turbine, and it's supposed to come out this way. One of the blades was lost. Actually, this is a picture taken outside of nCode's office in England. This particular blade here suffered a fatigue fracture, possibly due to cyclic loading from wind gusts or from inertial loading, from speeding up and slowing down as rotational speed change that can cause huge inertial stresses in such a large object. The majority of this one blade actually fell into the car park just outside nCode's office. Fortunately, no one was hurt, but certainly the ability for this turbine to provide its its design duty is nil. It's incapable of carrying on as it's supposed to. This one here is what we call Liberty Ship. This is a boat, as you can see, that's lost its ability to stay in one piece. This is an all-welded ship that was built by the United States in World War II, built very quickly by welding rather than riveting. The challenge there is that while welding is a great way to attach things together, it's also a great way to get that attachment to break through fatigue cycling. So in this case, the riveted joint, if a crack would start, it would not be able to pass through the lap joint into the adjoining member. However, with a weld, that is not the case, so this lacked the ability to deal with a crack, or to blunt the crack, or to stop the crack. This is not a fail-safe design. As you can see, this boat is seriously injured. At one point in World War II, some 30 or 40% of these boats that were in service had actually broken in half. That's certainly not a boat that I'd want to be on if I was in service. Lastly, down here in the corner, this might look like it, maybe not, but believe it or not, this is actually a filling in a tooth. And believe it or not, fillings in teeth are designed for fatigue, among other design criteria, fatigue, wear resistance, and so on. It's a pain to get a cavity, it's a pain to get a filling. So certainly we would not be happy if we had to go back and get a filling in another year, have it replaced, because it cracked due to cyclic loading from chewing. So believe it or not, cyclic loading and fatigue failures can appear all around us, which underscores the importance of understanding fatigue in an engineer or structural analyst's repertoire of engineering tools. So let's think about the actual definition of fatigue. What is fatigue? If you look in a layman's dictionary, you might find that fatigue is, quote, weakness in metal or other materials caused by repeated variations of stress. So weakness caused by repetitive stresses. Now, an engineer looks at that and says, okay, some English major wrote that, and that's fine. They're good with words. They can spell, but there's more technical detail to that, so let's think about that a different way. Let's be more specific and say it's the initiation and then growth of a crack until it reaches a critical size. So it's initiation and then growth of a crack until a critical size. And critical size can mean a lot of different things to different people. A crack in my sidewalk can be extremely long and not bother me. A crack in the crankshaft in my engine must be very short, otherwise we'll run into some serious warranty problems. So this idea of crack initiation and crack growth up until some phenomena that we consider to be failure is something we'll talk about a lot today. Other things to keep in mind with the definition of fatigue is that all fatigue phenomena are caused by cyclic loading. If the loading doesn't change, then we don't have a fatigue problem. When I say loading, actually I should be careful about that. If the stresses don't change. In this case of the bridge that I just showed previously, the loading may not change much. In that case, on the bridge, the biggest cycle of stress is actually caused by temperature differential, changes of temperature. So when I say loading, I got to be careful. I actually think it's the change of stress we actually care about. Change of stress could cause from change of solar loading, could be caused by vibration, could be caused by bumps in the road, and so on. The challenge in fatigue is that parts can fail even though stresses aren't that high. This can surprise people sometimes. When we say we designed this thing that it would never fail. In other words, the part won't yield in some static way, it won't fail. But even if the stresses are smaller than that, over time enough cycles can build up to cause a crack. This can be a surprise sometimes. So over time, fatigue cracks can start and grow large enough either to cause someone to be concerned because they can see it, or because the part actually breaks into two, which is equally a bad problem to have. So just as a review, a couple failure modes I've referred to so far. Some parts are designed with static failure criteria in mind. So if we plot out stress versus strain, think about this in a metallurgic sense. Most materials behave in an elastic fashion and then begin to yield. And then we have some point, if we continue to yield, we get more strain than stress. And in the end, we have some failure that can occur. This is not a cyclic load. This is what we call a monotonic load, a one-time application. continue to pull harder and harder and harder on the part, and at some point it can fail because some static yield or static tensile strength criteria has been exceeded. That's one failure mode. The failure mode we're going to focus on today is this one. What if the stresses are not very high? The yield stress, if we plot it this way, yield strength or tensile strength might be all the way up here. So we never get stresses that high, but the stresses change a lot over time. The stresses continue to change repetitively because of vibration, because of temperature change, because of loading and unloading, because of turning, because of hitting bumps, taking off, landing, and so on. So whatever caused the stress to change, it never gets that high, but if enough of these fluctuations or cycles occur, we may have failure happen over time in a way that we would not have expected simply looking at static failure criteria. We call this fatigue, from the French word for being tired. The concept of fatigue makes sense because it's something that happens over time. It's a little bit of a misnomer, though, because if you think about fatigue as a human person, to the human body, we think if we're fatigued, then we can get some rest. An over-the-road truck driver, for example, is limited to the number of hours that he or she can drive before they have to stop and take a break, and then they can continue driving tomorrow. That's to combat their own fatigue. In a metallurgic or material sense, there's no recovering from fatigue. So Germans, for example, they use the term Betriebsfestigkeit, which is a big one, as most German words tend to be, and literally that means operational strength. So rather than implying fatigue or recovery, they use the word strength in operation, a strength as the part is being used. So we got to think here about cycles. What causes stress cycles? How big are they? And if we can answer those questions, then we can use those as inputs to our fatigue life estimation technique. So let's think about fatigue cyclic loading. I've drawn a simple sine wave of stress here versus time. And let's just assume this carries on and goes on and on and on. Fatigue, crack initiation, crack growth is all driven by cyclic loading. So we have to have cyclic stresses or cyclic strains for fatigue to be a problem. If we have constant stress, this is not going to be our problem. Fatigue cycles, again, are defined by changes. This is really important, the word change in here. Change of stress or strain. It's not so much what's the peak stress or what's the valley or the minimum stress. It's the change between the two. So don't get caught up in saying this number here, the maximum stress, is key. What's more important than that is to think about if that stress can happen in usage, what else can happen in usage? Will our stress cycle go from maximum to say to 0, or maximum to some negative value with twice the change of stress? So reversed stresses can be a very big deal. Change of stress is what's important. We call that change of stress two things. We can call it stress range, which is numerically S max minus S min, or some people say, no, actually let's just call S max half that. We'll call it stress amplitude. The point is, it's the change of stress that we need to be worried about, and that is what we're going to track for understanding our fatigue calculation process. All right, so that's a cycle. So think about what stress cycles actually do. Stress cycles or strain cycles can cause cracks to start, and they can cause cracks to grow. So let's think about what this means. Cracks usually start at microscopic defects. On a microscopic level, if you look at a material structure, you'll find molecules, and you'll find what you may remember called shear planes or slip planes, or you might find discontinuities if you think back to your days if you've taken a class in metallurgy. All of those are prime candidates for cracks to start because they're weaknesses inherent in the substructure and microstructure of the material. Now, typically, we as engineers don't dig down to that level because it's very hard for us to do our jobs thinking about things on a nanometer level. So what we do then is we say, let's look at a crack starting, and then if we can see a crack, if it's big enough for us to see with the naked eye, say a couple millimeters long, then we'll assume it's a good-sized structural crack, and it behaves in a macroscopic way, after which we may have something like this. This is a specimen that was fatigued and broke. Crack started here, and you can see, might be hard in these pictures, but you've probably seen in fatigue specimens before, you have these things called beach marks. And what these are is this is essentially how much the crack grew each time. Just like the waves approaching with the tide coming up the beach with a rising tide, same thing here. This is the crack growing like this through this way until it finally got to the point where the crack was so big that the resulting its effect on the macroscopic structure of this was so large that the part actually failed. So crack initiation, crack growth, and this is what we call the fast fracture surface where it finally broke. So some parts, you think about it, the total fatigue life is actually built on two things. If you think about a part that's as produced, so straight up the assembly line, we have a part that's built. And 10 years down the line, it comes back to us as a warranty problem and it's broken in half. And we say, that wasn't supposed to happen, it broke in half. The actual life of that part, from a raw, virgin, pristinely produced part until broken in two pieces, was actually built up of two stages. Number one, a crack starting, like this, where we started with this raw piece of material with a hole in the middle because it needed that for clearance or something. And high stress is here and there, which caused the crack to initiate. And then over time, those microscopic cracks became macroscopic cracks to the point that the cracks got so large that this whole thing could actually break in half. And as a result, then, we have two pieces in our lap now. That illustrates the concept of total fatigue life. Crack initiation, followed by macroscopic crack growth, resulting in the actual whole life of the part. You may say, who cares? What's the difference? And you may not care, but I think that someone near you will care because different industries approach crack initiation and crack growth in completely different ways. Completely different ways. Some industries care a lot about understanding this. If we can see a crack here, this thing will consider it done. Customer's going to be mad. Right? Or some people will say, no. Crack right there is no big deal. Just as long as it doesn't break in half, then we're fine. So you think about some parts on an airplane, for example, or some parts on a bridge or on a car. There are some things that if someone sees a crack in it, it'll be considered a failure. Other things can have a crack. As long as it grows in a predictable way, we can allow that crack to grow because we know that we'll be able to take off and land and then inspect. So this concept of using these fatigue regimes, you could say, in different ways for different design philosophy is best highlighted by looking at two industries. Let's look at ground vehicles and let's look at aerospace applications. So first off, for ground vehicles, in general, this is really important here, I'll underline it. Whoops, this is not what I was meant to do. We'll try this. Okay. So in general, the just one second here. I've got something wrong with my presentation now. All right, we'll try this again. Okay. So the with ground vehicles, typically noticeable cracks are considered a failure. In other words, we're designing against crack initiation because on ground vehicles, typically, materials are quite crack sensitive. They're not crack tolerant. Crack tolerant materials tend to be expensive, and for economic reasons, typically tough crack tolerant materials like high strength aluminums and such are not often used in ground vehicles. Also, it's very difficult for us to require inspections for ground vehicles to say that after 50,000 miles in your $25,000 car, you need to spend $1,000 or $2,000 removing the interior, pull the carpet, and go off and inspect all the spot welds and structures and look and see if anything's changed. And if so, then we'll make replacements, or maybe we continue driving if the change is not very large. So in general, in the ground vehicle industry, we tend to consider noticeable cracks to be failure. Therefore, we're not concerning ourselves with crack growth, and we're designing up to this point right here. Let's not let a crack start. In contrast to that, on the aerospace side of things, Many components are made of tough, or what we call crack-tolerant materials. Toughness, by definition, is ability to be strong and ductile at the same time. You think about the area under the stress-strain curve is like energy. So the more ductile and strong material is, the more energy it can absorb before failure. So the aerospace industry says, we've got a huge asset here, $50 or $500 million asset, so we can afford to put some time into inspecting it. We also have a really severe loading environment. The performance boundaries, a performance envelope on a jet aircraft are extremely high because of, think about it, it needs to fly. It's amazing. So in that case, then, the industry often assumes that there's a crack, but let's analyze or let's design it so it doesn't grow in too fast of a way. So if we assume that there's a crack because of some manufacturing flaw or because of some environmental consideration, a bird strike or something, or a mechanic drops a tool and dents a structural member, let's assume that's a little crack, and let's design that member so that it won't grow so fast to cause immediate failure, but it will grow over the next year, for example. And when it does fail, it'll give some kind of warning, some kind of visual warning, or some kind of inspection technique will allow us to find it. So this requires frequent inspections, but with frequent inspections comes the ability to have a really good, you could say, understand the pulse of the, or the health of the aircraft, which can provide a very long service life with, in a very demanding environment. So, with this idea of crack growth and crack initiation, let's think about how we would analyze a fatigue problem. This is what we call the 5-box trick. This has been probably shown in a number of webinars that you may have seen with us here. This is our roadmap of how to do fatigue things. So we have 3 inputs on the left into some fatigue analysis, and we get some results. So let's define what these are. First off, for geometry, what we mean is we need to understand stress concentrations. You'll find through our discussion today that fatigue hotspots are always stress hotspots. Fatigue, as a matter of fact, is like stress raised to a power. It's like stress raised to, it can be quite a large power. So where stress is concentrated, fatigue damage is concentrated, and fatigue life is short. This is an example right here of one of the first commercial jetliners. This is called the de Havilland Comet. This is looking out the window. So this is inside the aircraft. This is frightening in one respect because this is a crack that's probably about 1 meter long, maybe even 2 meters long. This is miraculous at the same time too because it did not cause immediate failure. A wide variety, a number of these de Havilland Comets actually failed in a completely catastrophic manner. There was very little understanding of redundant load paths at the time, or very little understanding of the need for load and structural redundancy. So the problem was that this window was actually quite square, which led to a high stress concentration in its corner. Also, this is a jet aircraft, so for the first time it could fly very high, but to do so it needed to be pressurized for occupant safety. That meant then that there was a pressure cycle of 0 pressure differential through the skin when it was on the ground, to the interior being overpressurized relative to the 30,000 foot atmosphere when it was up high. So that cyclic load, pressure, depressure, pressure cycle, or what some in the aerospace industry call the ground-air-ground gag cycle, along with a high stress concentration, led to an absolute disaster. And this is the reason why we talk today about Airbus rather than de Havilland. So geometry is one critical understanding. Also, we need to understand the loading environment. What causes stress cycles? I'll say this several times today. How many cycles happened, and what size were they? How many cycles of what size? In this case, I'm drawing an example of a very simple stress cycle. Back and forth, back and forth. We call this a constant amplitude cycle. We'll look at other types of stress cycles in a little bit. We also need to understand material properties. This is what we call a strain life curve. We'll define this in just a minute. This is life in cycles down here versus the size of the strain cycle over here. So I can look this up in a handbook. I can find this in nCode software. I can run lab tests to derive this for material. It says this type of steel or this type of aluminum for this strain cycle size will last this many cycles to failure. Or conversely, if I want it to last this long, I better keep my strain cycle size below that. The material considerations are very important here. We can pull all those inputs together into a fatigue analysis. We'll talk today about three methods: stress-life method, strain-life method, and the crack growth method. And those methods with those inputs will give us fatigue results. How many cycles to failure, how many hours to failure, and so on. We have to keep in mind, though, that fatigue is a statistical phenomenon. It's not deterministic. So when I was in graduate school, we had I remember grading papers, and the solutions manual listed a solution to a fatigue analysis problem and said the problem itself was essentially estimate how long until failure occurs. And the answer there was listed in the solutions manual as some number with about 8 significant figures. It's like 410.857843 hours. Completely ridiculous, far more precision than can ever be hoped out of a fatigue calculation. Fatigue is a statistical problem because it's all about what's the chance of finding a flaw in the material in an area of high stress. So don't ever think that if we run 5 fatigue tests in the lab that they'll all fail at the same time. They may fail, say, within a factor of 2, or even a factor of 3, or in some cases even a factor of 5 on life. So we have this scatter band that we need to keep track of. All right, so that's our roadmap. So let's think about the methods that go in the middle, the fatigue analysis methods. We'll talk about 3 today. The first one is what we call the stress-life method. And it says that stress is what we will use to figure out how long until a crack starts. And for reasons we'll get into in just a little bit, you'll see that this works best for high cycle fatigue. Second method we'll talk about is called strain-life, sometimes called the EN method, E for epsilon, the Greek letter for strain. In this case, we'll say that strain drives crack initiation. And in that respect, then, we'll find out that this works for high cycle and low cycle fatigue. So this is a general purpose crack initiation method. Now you may say, hang on a second, stresses and strains, I learned about those. There's some letter number that relates those two. As a matter of fact, if you think hard enough, you might remember it's called the elastic modulus, or Young's modulus. And you'd say, wait a minute, aren't these doing the same thing? Stress life and strain life, wouldn't they be the same thing? We'll find out that they're not the same necessarily, because the elastic modulus is not the only thing that governs the relationship between stress and strain under all loading conditions. The last method we'll look at today is crack growth, which says we have a crack. How quickly does it grow? How long did it take to go from this nascent crack, this starting crack, to this fast fracture? How do we predict that? How do we understand if that's a day, if that's an hour, if that's a minute, if that's a second? How can we understand that? At what rate does this grow? Which is another way of saying how many beach marks are we going to have before failure? That uses this thing called the stress intensity factor. Rather than looking at stresses or strains, we're going to look at this new parameter called stress intensity factor, which comes from linear elastic fracture mechanics theory, and we'll dive into that in just a little bit. We're going to start, though, by looking at the stress-life fatigue method. So stresses driving fatigue, and it works best for high cycle fatigue. All right, so back in history here, this fine gentleman here, very scholarly looking. This is back when engineers wore suits and ties probably to go to bed at night. Very proper folks. This August Wohler is German, actually maybe Prussian, railway engineer, 150 years ago. Industrial Revolution, believe it or not, revolutionized a lot of things and introduced a lot of people to fatigue cycles, because suddenly there were things that could pick up tens or thousands or even hundreds of thousands of cycles per day through repetitive motion. Wohler's problem was a railway axle, train axle like this. It'd be mounted on the car this way. This is actually on a very primitive test bench here, but this in service would be mounted on a train car with the wheel out here, and then this connected to the bogie of the rail car up above it. So this thing, on a smooth track under constant load, the load would be constant because of the weight of the items it's carrying, but the stress on the axle, as the axle rotated, it'd be a reverse bending situation. So it's a rotating bending concept. And there were some surprises at the time that the axles would break after a while. Now, we've talked about the definition of fatigue already, so you can see where this is going. This needed some recognition of fatigue and a cumulative damage concept, or stresses aren't that high, but over time can still be a problem. So Voller wanted to answer these questions, and he made this test rig, as we see down here. This printout here actually is probably just about old enough to be in a wood carving. Actually looks like, it doesn't show up well on the screen, but this is his old-fashioned lab setup, and he's doing the best he could at the time. And he found out that if he put in a constant load, which meant a cyclically varying stress as the axle rotated, that after some time the axle would fail. No surprise. And he said, so each one of these dots here was a failed axle, and he found out that if he ran at different loads, or hence stresses, that axles would fail at different times. And you could plot it up on this curve like this, and you can see from this that the higher the stress going this way, then the shorter the fatigue life, which these days we take for granted. The higher the stress, the bigger the stress cycle, the shorter time it's going to have to failure. Now this is, you'd say, come on, why, who cares? That's easy. We all knew that. Well, once upon a time, F equals MA was radical 2. So even the simplest of principles needs to be validated. So Voller was the guy that did that. So he had then this chart he could carry around in his pocket. So if 1860s version of a design or designing engineer would come along, he could say, he could answer questions about if we want it to last some number of cycles to failure, then what should the stress range be limited to? Or vice versa, if we knew what the stress range was, then how long would we expect to failure? That was his SN approach. This guy named Baskin came along 50 years later and actually proposed a log-log SN relationship, a relationship between the log of stress, cycle size, and the log of the number of cycles to failure. And that led to what we call the proper SN curve today, which is created by taking a number of these specimens. Voller was testing axles, but we've since moved from testing whole components. Preferably, we'd prefer to test materials, so then when the component changes, our SN curve remains valid. So our approach these days is that we run a sample like this. This is probably about 4 inches long, half-inch diameter in the middle. There's some ASTM standards that say how to do this. We run a constant stress cycle on it, and we keep track of how long until it fails. And we can break a number of these under different sizes of stress cycle, and each one of those broken specimens will give us a little dot. So you can see there's some variability here, running at the same stress range, but we have failures that occur early and failures that occur late. That's why I say that this is a statistical, not a deterministic answer. So you can see now we have dots that are beginning to show a general trend of increasing stress, decreasing fatigue life. We can go one step past that then, and we can calculate a curve fit, which ends up looking something like this. This particular data set has more X's on it, which means there are more parts that actually failed in building an SN curve. SN curves are typically made by failing somewhere between 10 and 20 samples. Some people try to go as low as 2, right? So according to the letter of the law, if you want a perfect curve fit, you only get 2 data points and they fit perfectly. According to the letter of statistics, that's laughable. So the more samples, the better. In this case, following Baskin's approach of plotting the log of stress and the log of life, we can regress that, curve fit that with a linear regression, and we find out then there's usually a pretty good relationship. Now this is not the only way to fit an SN curve, but most typically a linear curve is fitted to the log of stress versus the log of life. Think about your math here for just a minute. What's linear in log-log space? An exponential relationship, power law relationship. So this says the size of the stress cycle is related to the number of cycles to failure by a power law relationship. B is the slope, the power, and sigma f prime is the intercept at one cycle to failure. So you should be able to look up then in a handbook or in nCode's materials guidelines or in your own company's material properties handbook, you should be able to look up what this value is for a material and what this value is for a material. And now we have an equation we can carry around that says the size of the stress cycle is numerically related to the number of cycles to failure and vice versa. This is the core of any stress life fatigue calculation. This one equation right here says if we know the size of the cycle, we know the stresses that happen, we can figure out how long it takes to fail if we know what the stress life curve is for this material. So this is the core of any fatigue calculation you do using the stress life curve, whether it's done by hand, whether it's done using a piece of software, or any other number of ways. So that, in a quick way, is the stress life approach. Again, stresses drive crack initiation, and for reasons we'll see in just a minute, this works best for high cycle fatigue, and it falls apart for low cycle fatigue. So let's look now at strain life fatigue. We'll look at strains instead. And there's kind of a real benefit for doing this. In many ways, strain life fatigue is the method that people have chosen as default for crack initiation over stress life because it can deal with low cycle and high cycle fatigue problems. So let's think about this then. So we talked earlier about materials, and if you were to look in a microscopic way, you'd find that a metal, most metals are actually crystalline. As a matter of fact, I think just about every metal I can think of is crystalline. So it's got some, you could think about it as kind of lumps or geometric entities that build up on these planes, right? And there are defects, there are molecules missing, or there are these things called dislocations or something, and those serve to limit strength, unfortunately. Parts, microscopically, materials don't fail because of breaking chemical bonds in tension, but rather by sliding them past each other, by shearing. So really you can think about, in a microscopic way, the material is like a deck of cards. And if I take this deck of cards and I put my hand on the top and push that way, and do the same thing in the opposite direction down below, if I shake my hands back and forth, move this deck of cards around, over time the cards will slip relative to each other, shear past each other, and we have this. In a microscopic way, this is the start of our crack. So this is the onset of crack initiation. So you think about it then, what is it that best describes this phenomena here? Is it how hard I push on this, or is it how much it's moved? The answer is, it's how much it's moved. Strain is the key driver. How much is this material being deformed? So it's strains that we actually care about. Strains are the best way for us to visualize what's happening to our microstructure. So cracks start with this microscopic deformation. Deformation is the key word. Remember, stress means how hard you're pushing or pulling or shearing something. Strain means how much it's moving in relation, how much it's deforming. So strains seem to make sense here. Well, stresses and strains are linear related sometimes. Other times they're not. If we get into large stresses, then we can end up with a nonlinear relationship between stress and strain, which means then that when we get into large fatigue cycles, the stress life method is tracking the wrong parameter. We should be tracking strains rather than stresses. So we need to track strains if we want to understand large fatigue cycles. So really, stress life method is tracking the wrong parameter, but in some cases it gets it right because of a linear elastic relationship. As we move out of high cycle fatigue, though, that behavior, that linear elastic behavior can disappear, and that is why the strain life method is preferable. As a matter of fact, it works for high cycle and low cycle, whereas stress life begins to produce some really ridiculous answers when you get into low cycle fatigue. So strain is the right thing to track here. So the way we do this, we're going to build up what we call a strain life curve. You'll see a slide of a strain life curve in just a minute. There's a standard that says thou shalt do it this way. This is a similar type of test specimen. It's a typically several inches long with a half-inch neck section in here to concentrate the failure in this location. This thing is called a clip-on extensometer. It's essentially like the world's easiest to use strain gauge. You can actually just rubber band on with dental rubber bands onto the part, so it's very easy to monitor strain in the part. That means then when we're cycling the test article, if we want to break this thing and see how big was the cycle and how long did it last, we can actually run this thing in strain control, which is great. Because remember, we said that strain makes more sense to understand microscopically what's driving a fatigue crack, what's initiating this crack. So from this, we can build this thing called the strain life curve. Some people call this the EN curve. And it plots, like a stress life curve, it plots the size of the fatigue cycle. Now this is given in strain rather than stress. And it plots on this axis the life, how long until it fails. Now one little bit of confusion is that this is now plotting strain amplitude rather than range. The difference is a factor of 2. And just to further confuse the issue, this is now not cycles but reversals, and we have 2 reversals per cycle. So there are these factors of 2. If you're doing these calculations by hand, those factors of 2 can be a real pain. If you're doing them with a piece of software like nCode, don't worry about it, that's all handled for you. What this curve shows us, what the strain life curve shows us, is much like what the stress life curve shows us. As the size of the cycle increases, the life decreases. But it's interesting to look, there's a knee in the curve. There's a bend here. This is high cycle fatigue, and this is low cycle fatigue. So this is essentially the stress life curve converted into strain space with elastic modulus. And you can see then, as the strains get larger, as they are wont to do after plasticity, right? We can see then that a different slope begins to control the fatigue curve. The red curve is the total strain life curve here. Mathematically, it's given this way. It says the size of the strain cycle and the number of cycles to failure is related by not one, but the addition of 2 power law relationships. So now we'll have how many constants? 1, 2, 3, 4, 5 constants that relate life and strain size. And actually behind the scenes, there's another thing called the cyclic stress strain curve that we need that will give us 2 more fatigue properties. We're not going to get into that today just in terms of time. But again, this is the core of any strain life fatigue calculation, this equation right here. For a given material, we can use this curve to tell us, if I know the cycle strain size, how many cycles of that until failure. This is actually a real pain to solve by hand because this is a very nonlinear relationship. This is a difficult equation to solve for NF because of this nonlinearity. So this is where I like to say, if I want the wrong answer, I'll do it by hand. If I want the right answer, I'll give it to a computer. But this is the core of the strain life method. Now let's move on and look at crack growth. How long did it take, or how long would we predict it would take for this crack to proceed through here, and what keeps it from growing further? Why doesn't this crack just march on through all the way this way? Why does this fail in one fell swoop in what we call fast fracture? Why does it fail so quickly? So to understand cracks, what we have to do is think a little bit differently. We've been looking at stresses and strains on, by default, the uncracked continuous media. So linear elastic stress strain theory. Now we have a crack, and a crack is the worst kind of stress concentration ever because it's really, really severe. As a matter of fact, a crack, by definition, is an infinitely sharp, 0 radius on the end here. Radius goes to 0, which means then that theoretically the stresses should become infinite there. Now that's not really possible because of yielding and such, but it certainly points out a problem, and that is that if we look at stresses on cracks, we can drive ourselves crazy because this all falls apart at the tip of the crack. So we need another way to understand stresses on cracks. That leads to a thing that we call stress intensity factor, and it's given the letter K. We'll see the definition of this in just a minute. This all comes from what we call linear elastic fracture mechanics, which is like elasticity theory, but in the presence of a discontinuity in the presence of a crack. So linear elastic fraction mechanics says this: the stress intensity factor K is related to a few things: a geometry factor, the applied stress, the length of the crack. Remember this letter A, this is the length of the crack. And then just to show this is derived from some mathematical equation, there's square root of pi. So just as a note to yourself, if you ever want to derive a mathematical equation, I would certainly use pi in there somewhere, because then you can say it comes from basic theories. So what this says is the higher the stress and or the longer the crack, the more serious the crack driving energy is, the stress intensity factor is. This geometry factor, you can look this up in the handbook. The stress is like P over A on this. This is nominal stress. And then A is the small a, is the length of the crack. And we find out that if the stress is very high, or if the crack is long enough, that this value of K can actually get very high. As a matter of fact, it can get so high that the crack doesn't grow. You could say that fatigue life is one cycle failure. It's what we call fast fracture. So this is a material property called K1C, K1 critical. You can look up in a handbook, and then if the stress and the crack length and geometry all come together and this exceeds K1C, then that means it fails immediately. This is not a crack growth problem, or maybe you could say it is, but it's only one cycle failure. So you could use that as a failure criteria. Don't let the crack get too long to cause fast fracture. And if it doesn't fast fracture, then every cycle can cause the crack to extend just a little bit longer. And that brings up this thing that we call the crack growth curve. And the crack growth curve looks like this. It says that the crack growth rate per cycle is related to the stress intensity factor range. It's called a dA/dN delta K curve. dA is change in crack length. dN is change in cycle. So this is crack growth length per cycle, crack extension per cycle, versus the size of the applied cycle. Not stress, but this actual stress intensity factor. So this curve here then tells us that if we know how long the crack is, and we know the stress on it, we can come up with the stress intensity factor. If that, as a cycle of that occurs, we can figure out the range of that. We can look on this material curve and say, look across here, it says its crack is growing right now at a rate of 10 to the minus 4th millimeters per cycle. And this is a nice, what we call a stable growth region. As the crack gets longer, it tends to accelerate. This crack growth is an example of a positive feedback system, where the longer the crack is, the worse it grows, which makes it longer, which makes it worse, and so on. And it will finally fail if the end game here that sets how long can the crack actually grow to is when does the crack and the applied stress on it lead to a stress intensity factor that's greater than K1C. So that's the end of the game. So for crack growth, this is the basic formulation of how big is the cycle and what happens next, just like the stress life curve and the strain life curve did for us as well. So now let's see how we put these things into use. Any of these three methods, how do we actually put them into use? So let's look at loading, at cycles. Here's an example of what we call constant amplitude loading. This is stress varying from plus to minus some number of times. Okay, that's fine. We could use this with a stress life curve, with a strain life curve, the crack growth curve, to say if this cycle occurs repetitively like this, how long until failure occurs. The challenge of this is that very rarely is our stress history or our cyclic loading this simple. More complicated example would be this one, where we actually have different sizes of cycles occurring. For example, in a railway axle, this would be going down an infinitely smooth, perfectly smooth track with carrying one load. This is carrying a moderate load, and a smaller load, and a much larger load. And the amount of time spent doing one versus the other can be quite different. This is what we call block loading. Even that's a simplification, though. Realistically, if you measure stresses or strains in situ, you'll find it looks something like this. And we call this variable amplitude loading. It looks kind of random. It's really not random. Mathematicians get excited when engineers use the word random. But it looks quite random because it changes quite a lot. And the question is then what cycles are inside there? And that leads us to asking questions about what's really important about fatigue cycles. And then by extension, what does that mean relative? How can I understand what that actually means? Someone once told me that if you want to really reach out and grab an audience, you need to talk about money. Everyone understands money. Not everybody understands crack growth rates or J integral or stresses or strains. So we'll throw money in here in just a minute as well. Important factors in fatigue are these. The size, excuse me, the size of the cycle. How much does the stress or strain change? Peak stress is not enough. A reversed cycle is different than a zero tension cycle. Cycle size is important. Secondly, how many cycles occurred? Were they all the same size or were they different? So if we can answer these two questions, regardless of loading history, if we can somehow condense a stress history down to how many cycles of what size, then we're in good shape. This is very similar to your bank account. If you're not working, if you don't have any ability to recover your monetary losses, your expenditures, say you have a trust fund, then every time you make a withdrawal from the bank, we need to think about two things. How big was that expenditure, and how often does it happen? If we know those two things, how much did we spend each time, and how often does it happen, then we can look and see how long can we keep spending that way. And we may have different types of expenditures. We may have mortgage payment. It's excuse me, a big one that doesn't happen very often. A car payment or several car payments that aren't so big but they happen more frequently. And then maybe dinner, lunch, $10 a pop. If you go out 5 times a week, that can add up as well. So we can think then that if you spend all your money, you're broke. The exact same thing happens in fatigue. It's a cumulative problem. Fatigue is a cumulative problem where each cycle has the ability to somehow further this fatigue problem, or conversely, to shorten fatigue life. So that means then that we need to think about how many cycles of what size and what do they do together. How many cycles of what size is answered best by a technique called rainfall cycle counting. So if you take your stress or strain history and turn it on its side, as shown up here in this blue squiggly line here, we can take this and imagine rain falling. Imagine this is like a pagoda roof. Rain drips and falls off and so on. Depending on how the rain drips, we get fatigue cycles, or the rain keeps going and the cycles are used elsewhere. If we plot out stress versus strain space, we get these things called hysteresis loops, which, believe it or not, actually shows up as our logo here. We actually have 4 fatigue cycles, 1 big one, 1 medium-sized one, and then 2 small ones. So rainfall cycle counting, as weird as it sounds, rain dripping off a roof, that has absolutely no physical relationship to hysteresis loops, but coincidentally is a great way to visualize how hysteresis loops open and close. So rainfall cycle counting allows us to deal with these stress-strain loops. It can find these fatigue cycles. So this is a really great way that we can use for strain life analysis, for stress life analysis, for crack growth analysis to find fatigue cycles. This is a really nice method. Computers do an awesome job with this. It's a very efficient little pile of programming to enable this little algorithm to come along and work. In the end, we can look at something like this, which is a record of cycles. This is the number of cycles on the vertical axis, and this is how big are the cycles going this way. So the cycles that happen most frequently are the tall towers, and fortunately they are quite small. The larger cycles happen less frequently, to the extent that the biggest cycles we hope don't happen very often at all. This is just like your expenditures. This is mortgage payments, car payments, dinner, lunch, and bubble gum. Or driving into work, this is expansion joints, left turns and right turns, flying over the railroad tracks, or your teenager driving on Friday night. So with an understanding like this, we have a way now of understanding how many cycles of what size, and that will lead us into what we call Miner's rule for damage accumulation. So let's think again back to this cyclic stress history. The stress life curve, or the strain life curve, would allow us to say if the cycling was just like this,
how long until failure occurs? Or, if stresses were just like this, how long until failure occurs? But what we've missed so far is what happens if the stresses are like this for a while, and then like that for a while, and then like that for a while. This leads to damage accumulation and Miner's rule. Each one of those cycles we can look up and see for cycle size S1, it's allowed to happen that number of times. That looks like about 50,000 cycles to failure. We call that NF1. It actually happened 1, 2, 3, 4, 5, 6, 7 times. So we're actually like 7 50,000ths of the life used up just by that little block. Likewise, we can perform similar calculations for this and for this. And what Miner's rule says is that all of these add up together. We have these partial damages, they're called. The amount of fatigue life used up, or what we call damage, is numerically equal to the number of times a given cycle occurred, 7 times, divided by the number of times it was allowed to happen, 50,000 times. This one happened 10 times, and it was allowed to happen 100,000 times. That allows us to fill in this partial damage fraction. This one comes from S1, from S2, S3, and so on. If the total damage is equal to or greater than the 1, that means we've used up the expenditures. We've completed our life. Fatigue failures occurred. If, on the other hand, as we hope, fatigue damage is a small number, that means we can continue to repeat this entire history. And that allows us then to say how many thousands of repeats or laps or hours or something to failure. This is Miner's rule in action. So we've looked at how to understand cycles, understand material properties, looked at how to accumulate damage according to different size cycles, and so on. What we're going to do now is look at how do we actually apply this in an engineering sense. 2 ways. One way is to use measured strain gauge data. That's what we see right here. This is an actual physical prototype with a strain gauge on it. We can go out and drive that, record stresses and strains over time. Or we can use FEA. It's the exact same part. It's just a virtual model, virtual part, which means then we can recover virtual stresses. So 2 different ways to approach this. To use measured strain gauge data requires us to bond strain gauges to the part, and then from the resulting stress or strain history, we can predict fatigue life in those critical locations. What's nice about this is people have been doing this for a long time, so it's accepted historically. Strain gauges measure measure stresses or strains under a wide variety of conditions, linear, nonlinear, vibration, temperature related, and so on. Disadvantages are that we need to put the strain gauges in the right spot. We need to know where the critical locations are. If we have 10 critical locations, we need 10 strain gauges. And that can lead to quite a bit of labor in some cases. We need a gauge for each hotspot. The strain gauge that we measure has limited shelf life if the design changes. So if the part changes drastically and the load paths change, then the structural response we measured is no longer valid, so we have to be careful with that. And then lastly, this requires a working prototype that we can measure strains on. This is obviously what everybody wants to get away from these days. Want to do as much digital work as possible and do only the physical prototype work that's only absolutely required to validate calculations that have already been done. As a matter of fact, you can look at this a different way. There's nothing more expensive to your design process than building something just to watch it fail. That can be a very expensive proposition. Which leads us then to looking at finite element-based fatigue analysis. This is a finite element model up in the corner here. The idea here is that we use FEA to predict stresses and strains. We can determine virtual stress cycles that way then, and we can predict fatigue life for the whole model. We can turn on our model in a stress plot like this into a life plot, a life contour plot, using these fatigue concepts. The advantage of this is a huge one. Like I said earlier, everyone wants to get away from building physical prototypes, do as much digital. That way we can quickly make changes and understand differences in design. FEA is widely accepted these days. A wide variety of FE solutions are supported. Linear, nonlinear, transient, dynamic, modal, frequency domain, and so on. All of these are
are viable ways to understand stress these days. Disadvantage, though, is that we need good hotspot stresses. If your model's not capable of predicting stress, it will certainly not be able to understand fatigue life, since fatigue life is very, very closely related to stresses. And also the real world can be very nonlinear, which can lead to calculation difficulties sometimes. So we can apply those concepts inside software using nCode. The nCode software, we've been doing fatigue software for 30-some years now. We've got a couple of different products to address this. We're going to look very briefly right now at using GlyphWorks for measured strain gauge data and using DesignLife for finite element derived or virtual stresses and strains. So let's just take a quick look at this. Let me just jump out of this and see if I can bring up my other application. That would be this one here. And what I have is running a little bit short on time. So what I'm going to do is I'm going to open up strain gauge fatigue process I created earlier. This is a process I create with these functions called glyphs. Just based on time, I can't get into detail of what all GlyphWorks does. This is supposed to be a conceptual webinar today, so if you need more information about this, let us know. We can help you. Also, our archived webinars have a great amount of detail on different use cases for this particular type of calculation in GlyphWorks. So I have some strain gauge data here. These are strain gauge channels versus time, a series of hotspots, actually 5 separate strain gauge readings, 5 separate hotspots. And I've plugged them into a fatigue calculation in here. I've associated material properties and such. I'm just going to run this so we can stay on track here. And what I end up with then is a separate fatigue calculation done for each strain gauge location, each hotspot. You can see that it's calculated, it's counted 20-some odd thousand cycles for each of those strain histories and calculated fatigue life for each one of them independently. So we can see the shortest fatigue life is 16,000 repeats. That's repeats of this time series right here. Or that's also calibrated into hours as well based on the duration of the time that's recorded in the time domain. We can also get total damage and damage per hour. This plot here shows us the rainfall cycle count, how many cycles of what size, and down below how much damage was caused by each of those cycles. If we were to total up the damage from all these bins here, we'd get back to this, because after all, that's what Miner's rule says. Linear damage accumulation. As more cycles occur, more fatigue damage accumulates until the possibility of fatigue failure exists as well. So this is very briefly how we might approach the question of strain gauge-based fatigue. I'm going to look at a different process now, and that is, let's look at this one. I'm going to look at a different process for working with finite element results. And that process looks like this. Same idea, except that rather than measured stresses and strains, I actually have a finite element model. So this time in my model, I actually have, this has been solved for stresses for 2 separate load cases. One of these is the vertical Z load. Let's see the stresses like this. So that's the unit load of hold one end and push on the other. The second load case that was solved is this one, which is, as you can see from symmetry, hold this end and then twist this direction. So 2 separate load cases were solved. Those are static stresses, so fatigue is not going to be a problem then, right? The question is, what causes those stresses to change? And in my case here, we have a number of ways of making cycles. In my case here, though, I actually have someone measured the actual vertical load versus time and the moment versus time. So as this will change, the stresses will change from that loading condition. And also, this will cause stresses to change as well. DesignLife puts those two together. So it does a linear, it does a superposition of stress from side loading in addition to stress from the twist. And inside this glyph, I've got that set up, and it does, it's got a material curve built into it and such. I'm just going to go ahead and run this. And you can see what we've done here is this plot now is a fatigue life contour plot that shows that the minimum, if that was 1 lap of the proving ground, then we're predicting about 2,800 laps to failure. So really, each and every node here is acted as its own virtual strain gauge, you could say, and that way we can monitor hotspots in the whole model rather than just wherever the strain gauge was placed. So that is a really quick look at